So in this exercise, we're given a system, and several of the characteristics of the system are known, but there are also many that are unknown. So what they're asking us is that from what we are given here, can we determine all of the unknown voltages and currents? So let's take a look at this and see what we can figure out. So the first thing we notice is we have I1 here that is an unknown. However, we do have in the same path, so I1 has to travel all along this path here because there's no other way for current to leave or enter that conducting path. So whatever I1, it has to be a value that creates a 6-volt drop across a 2-ohm resistor. Well, this is basically just an application of Ohm's law. So if we look at it from that regard, we can calculate I1 then by just using V over R. And this is again from Ohm's law. And so in this case, as we follow along the path that the current's defined as, and so we see it defined right here, that's the direction of travel, the way I've drawn it here. If we do that, coming along here, we see we encounter the negative sign first. So that means it's going to be a negative 6 volts. And then the resistance of the resistor is just an absolute number, so it's over 2 ohms. And so that's going to equal minus 3 amps. And so the reason this is minus is because it's in the opposite direction of the way that it's shown here. So let me clean this up. So you can see that we define the direction as this way for the current, but in reality, it's traveling that way. So that's why it's a negative 3 amps. So that's I1. So now we want to look and see what else we can calculate here. And the next thing that pops up is we have I2. Okay, so we know I1. So let me get back over here. So we know the value for I1 now, and we know this value here. So we know that all the currents leaving and entering this node. So that being the case, we should be able to apply Kirchhoff's node analysis and determine what the currents are. So if we sum up all the currents leaving or entering that node, it should equal to 0 if we use Kirchhoff's analysis. So that being the case, we're going to arbitrarily pick a direction that says all the currents leaving the node should equal to 0. So that being the case, first we know what that means is I1, and this is again, we're stating all currents are leaving, so that's positive direction. So I1 plus I2 plus I3 has got to equal to 0. Remember, that's Kirchhoff's law. So in this case, being that we've defined the direction out from the node, I1 then would be 3, positive 3, because it is actually going out from the node. So then we got plus I2. We're showing it leaving the node. We're showing it here, the direction out. And then 2, this is I2. And then we're showing 2 as leaving out of the node as well. So then that'll be plus 2. And that's all got to equal to 0. So now if we solve for I2, what we'll have then is I2 is equal to minus 3 minus 2, so that's minus 5 amps. So that's I2. Okay, so what else do we not know? Another unknown we have is this V sub D. We don't know what that is. However, we do know that we have 2 amps, because it's given to us here, flowing in that direction. So that's in the positive direction. So we can use Ohm's law again to determine what that value is. So if we do that, we'll say that VD is equal to 4 ohms times 2 amps. So that will give us 8 volts. Okay, so to clean up some space here, I'm going to rewrite this up here. So we know I1, so we said I1 is equal to minus 3 amps. And then here as well, we determined I2, so I2 is now equal to minus 5 amps. And so that just means that we're showing the wrong direction, right? If it's minus 5 amps, the current's actually flowing that way. And then we just calculated V sub D, which we said was 8 volts. So now I want to give myself a little more room here. So another unknown that we have is this voltage here, V sub B. So V sub B, the voltage across V sub B, which is here, going from this direction to this direction, should equal to the same voltage as going around this loop and getting to that same point. It's got to be equal. So the only things we have going in this direction is this known voltage, and we calculated VD, so we should be able to determine that. So if we look at that, then VB should equal to VD plus 4 volts. So we can see we hit the positive sign first as we're traveling this direction, so it's a plus 4 volts. So we know what VD is. VD, we said over here, is 8 volts plus 4 volts, and so that gives us 12 volts. So now we know what VB is. And so finally, the only unknown we have is this VA. So VA, we know what the voltage is. Let me clean this up a little bit. So now we know what the voltage is at this node, that's VB, and we know what the voltage is here. So we should be able to determine the difference between those two to give us VA. So doing that, we'll say that VA is equal to VB minus, because as we go this way, it's going against the positive, so minus 6. So if we plug that in, we just determined that VB was 12 minus 6. This should equal to 6 volts. So again, I'm going to just rewrite these over here. We've got VB, we said was 12 volts. And then we have VA, which we said is 6 volts. All right, so we've determined all of the unknown voltages and currents in part A. So these right here are the answers to part A. So part B, they asked us to find the power flow into each element. So to do that, we recall that we have our power equation that we can utilize. And so the general form is P equals to VI. But if we substitute Ohm's law in there, we can come up with some different forms like I squared R or V squared over R. All of these will give you the same result, and they're just substituting different things in from Ohm's law for voltage and current. So let's look at each component now. Power for the 2 ohm resistor. So that is this guy here. So to do that, we know what the current is, we know what the resistance is, so we should be able to utilize the I squared R. form of this equation. So the I is I1, so it's going to be minus 3 squared, and the resistance is 2. And so when we calculate that out, we should get 18 watts. So that's through the 2 ohm resistor. So next, we've got the 4 ohm resistor, which is right here. So for the 4 ohm resistor, we can do the same type of thing. So I will put that one here. And power through the 4 ohm resistor. Again, we know the current, so we can use the I squared R form of that. And so the current was 2 amps. So we square that, and then the ohms was 4, or the resistance of 4 ohms. And so when we calculate that out, we should get 16 watts. Okay, so far so good. So next, we want to look at this A component right here. So for the A component, we know what the voltage is now, that's VA, and we know what the current is. So we should be able to utilize that to calculate what PA is. So PA, that's going to be, we're going to utilize the VI form of that. So in this case, it's going to be a negative VA because of the direction of the current flow, and then times I1. And so that will give us a minus 6 volts times minus 3, and that gives us 18 watts. All right, so we're making pretty good progress now. So now we want to look at this component B. Excuse me. So if we look at that, B, so we'll do that one here. So the power for B, so what do we know about B? Again, we know the voltage, VB, and we know the current, I2. So we're going to use the VI form again, and that's just going to be VB I2. So from our part A, we see that VB is 12 volts, and we see that I2 is negative 5 amps. So that gives us a negative 60 watts. Okay. And finally, we've got C, PC. So that's going to be, run out of colors here, so I'll just do yellow again, PC. So I'll put that on the same line as the yellow dot, just because we're running out of colors here. So we've got PC, and in this case, we know the voltage and we know the current. So again, we'll utilize that. And so the voltage was 4 volts, and the current is 2 amps. That's a given, and so that's 8 watts. So there's the power flow through all of these. So one quick thing we can do as a check to make sure this checks out is we've got to conserve energy. So if we add up all of our power, it should equal to 0. So in this case, we've got the 18 watts, and we've got the 16 watts, and then we've got another 18 watts, and then we have a minus 60 watts, and then we have an 8 watts. And when we add all this up, you plug it in the calculator, we do in fact get 0. So the energy was conserved, and this checks out.